Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be starting our discussion on the case of Hamilton's principle, and slowly we will go towards the derivation of Hamiltonian. So the Hamilton's principle in a very quick format mentions that the variational principle is equivalent to the Lagrange equation of motion. So that is my Hamilton's principle, and we can look for the variational. So the Hamilton's principle says that. So again, before writing this Hamilton's principle, I think I should have mentioned what is the variational principle. So the statement says the variational principle is that the actual behavior, the variational principle mainly states that the actual motion of a system is completely determined by the solution of the functional, which makes the functional stationary, right? I think that is a fairly intuitive statement of variational principle. So all it says is that if you are given a functional which is given by this, then whatever makes this functional stationary, and of course this is going to be the case when Euler-Lagrange equations of motion are satisfied, then that extremal or that solution to that functional is going to make the functional stationary, right? And that is the actual motion of the system, and so that is what it is. So then the Hamilton's principle says that this Euler-Lagrange equation of motion is nothing but the Lagrange equation of motion, right? So somewhere we are inherently stating that we are trying to extremize the functional that we are trying to extremize. F is very much identical to the Lagrangian L, right? So let me slowly try to formalize this thought. So let us say we consider system with 1 degree of freedom. Okay, 1 degree of freedom. And let us say we consider a Lagrangian with a single coordinate, generalized coordinate q, right? And what we see is that L of q comma q dot comma t is going to be, so what is it? So if we were to write the equation of trajectory, then the trajectory q star is going to be d dt of partial L partial q dot minus partial L partial q is equal to 0. So that is the trajectory which satisfies the Lagrange equation of motion. Okay, and or otherwise it means that whose solution, the solution to this Lagrange equation of motion is going to makes the integral s of q to be integral from t0 to t1 L of q comma q dot comma t dt, this integral stationary. Okay, so the trajectory which is the solution to this Lagrange equation of motion will make this integral stationary, or which will be the extremal to this integral involving the Lagrangian. which is what I said few minutes back. So then, as I'm repeating the Hamilton statement again in terms of this Lagrange equation of motion. It says that the Hamilton's principle Q star is an actual motion of the system, if and only if it makes the action functional S of Q stationary. Action functional stationary. Okay, so let us look at an example for this Hamilton's principle. So the example that I have is that of an oscillator. So the problem says certain oscillators with coordinate Q, the oscillators with coordinate Q has Lagrangian, which is given by L of Q comma Q dot comma T, which is half Q dot square minus half Q square. So that is my Lagrangian with Q as the generalized coordinate. So one variable Lagrangian, right? So there is no explicit T dependence. Now further we need to verify in this problem, we need to verify that Q star is sine of T, and this is a motion of the oscillator, and show that it makes the action integral stationary. Okay, so this is what we have to find. Well, I'm already given the solution. I have to show that it is the extremal to the functional. Okay, so what is, I think I haven't mentioned what is action integral. Action integral is the integral which I have mentioned. So this is the S of Q. S of Q is the action integral. Okay, this is what we have. Okay, so then if we have this Lagrangian given by Q dot square minus Q square by 2, then if I were to differentiate d dt of partial L partial Q dot minus partial L partial Q, right, and we were to evaluate this Lagrange equation of motion, I get that Q double dot plus Q is equal to 0, and in this case Q star satisfies this equation. Satisfies. Well, what is Q star? Q star is sine of T. So one solution to this equation of motion is sine T, and then we have to show that further if we were to see what is the sign of the functional. So suppose we were to find S of Q star plus H, the sign of this difference, S of Q star plus H minus S of Q star, then we see that this is half integral 0 to tau cos of E plus H dot. So Q star is sine T, and then S of Q star is, we plug it here, so H square, and then minus sine T plus H, then minus cos square T minus sine square T, right, and this is dt. And we see that this integral half, this integral comes out to be, if we were to simplify everything, what we get is integral from 0 to tau 2 H dot cos of T plus H dot square minus 2H sine T minus H square dt, right? And if we were to integrate it out, we see that this first integral, if we do the integration by parts, the first integral and this third value will cancel out each other, and what we get is that we are reduced to the following integral: half h dot square minus h square dt. Just please, the listeners are requested to please integrate the first and the third functions in this integrand, and they will cancel out, and subject to the fact that h at the end points are going to be 0. So this is what we have. And now if we were to find an upper bound, the upper bound of this integral is so this is from 0 to tau. If we were to find the maximum of h dot and the maximum of h, this is going to be tau by 2 times the order of h, the order of h square and h dot square. So that is the order of the two functions. And so what we get is that this functional is of order h is norm of h square, right? So norm of h square. So let us so order of h, what is h square? Norm of h is the max of both h dot and the max of h. So the max function, we have defined this norm, and then we see that indeed sine of t is going to give us the extremal. So all that is of course we are, so that is what we have. So we have found an extremal to this function. Okay, so now how about Lagrangian of several variables? So Lagrangian of n simultaneous equations of motion. So we have partial t of partial L partial Qj minus partial L partial Qj. This is equal to 0. So j is from 1 to n. And now what we see is this is for each j. So now we are talking about a generalized coordinate vector which is q1, q2, qn. And we see that we can write the action integral. We see that this is s of q given by integral from t0 to t1 L of q comma q dot comma t dt, and we see that so that is the action integral. Now again we can similarly define the stationary point of the action integral. The stationary point is when let me write this statement. So stationary point for s of q. S of q is defined to be the vector. This time it is not a scalar but a vector. So a vector function x star of t which makes this functional, the functional j of x stationary, makes this functional stationary if we have j of x star plus h minus j of x star is order of h square. Okay, so then this is when h is this norm of h is small. This is small. Okay, so so this is the most general definition for the stationary point of an action integral. And Hamilton's principle is again for n variable case, the Hamilton's principle is also identical to that of a single variable case. So this is identical to one variable case that we have written in the previous slide. One variable case. with q and q bar, one variable replaced by q bar. Okay, so then what we have is, so this question is, what exactly, I think few modules back, we had potentially highlighted the superiority of Hamilton's principle versus, or Hamiltonian, the introduction of Hamiltonian, or the introduction of calculus of variation versus the Newtonian mechanics. So let us write down and let us highlight the difference as well as the superiority of doing, or approaching the problem using the Hamilton's principle or the calculus of variation. So the idea is, why go through so much pain when the Newton's equations of motion is present? The fruit or the success lies in realizing the significance of Hamilton's principle. Okay, so the Hamilton's principle can be considered as a more fundamental postulate than Newton's law. Why? Because we will see that Newton's first of all, it can be an alternative to Newton's law. We have seen the Newton's laws of motion can be derived using the Lagrange equation of motion, but also we talk about we talk about the invariance, or we talk about the Hamilton's principle in generalized coordinates. And whenever we talk about the system in generalized coordinate, because of Noether's theorem, we have the invariance of the coordinates. That is, the action integral is never changed with the invariance, right? And that is not exactly present in the Newtonian theory, right? So let us write down these facts. So the first of all, we can consider Hamilton's principle as a more fundamental postulate than Newton's law. The more fundamental postulate than Newton's law, and it is an alternate route to Newtonian theory. And what the major advantage is, the presence of invariance in the Lagrange equation of motion. So the invariance with respect to the generalized coordinates. So what we get is that if the trajectory q makes S of q stationary, makes our action integral stationary, then the corresponding invariant generalized coordinate, the corresponding q prime of t, which is the invariant coordinate, will make the corresponding action integral S of q prime stationary. Okay, and which means that the extremals, it turns out that the extremals they match. They will map. The extremals of S of q, they map onto the extremals of S of q prime. And this sort of a particular property of the invariance of the action integral is nowhere to be seen in the Newtonian mechanics. And that is why it turns out, using this invariance property, we can greatly simplify our problems in the Lagrange equation of motion. So that exactly sums up the specific advantage of the Hamilton's principle. So now let us we have few more minutes to this module. So let us now consider consider the presence of continue our discussion on the Hamilton's principle. Especially, I would now slowly start to incorporate and introduce the concept of Hamiltonian, right? And so what we want to do now is we will introduce the concept of Hamiltonian, and alternatively we will also introduce the Hamilton's principle, and the equations of phase space, the Hamilton's principles and the equations of phase space, right? So the key concepts that we want to study is the Hamilton's phase space. So what are the phase space? Again, when we revisit, when studying the Hamilton's phase space, we will revisit the concept of generalized momentum, right? And then we will also look at a result in the form of Liouville's theorem, Liouville's theorem and recurrence, Liouville's theorem and recurrence, and we look at the second order Lagrange equations, which Lagrange equations are second order PDEs. So it turns out that using Hamilton's principle, we can reduce the Lagrange equation into two first order PDEs, two first order coupled ODEs, and so on. So for a system of n second order PDEs for Lagrange equation of motion, we can reduce it to 2n first order ODEs for the Hamilton's equation. Okay, so what I'm writing is the same statement. The second order Lagrange equation can be reformulated as a set of first order ODEs as Hamilton's equation. Okay, so converting, just a very brief example as to how to convert second order ODEs into first order. Let us just look at an example. So the example that we have is converting higher order ODEs to first order, the first order ODEs, right? We see that if we consider the oscillator x double dot plus 3x dot plus 4x, this is 0. This is a second order ODE. So then suppose we introduce a new variable. We introduce v, which is x dot. We introduce a new variable. We see that x dot is equal to v, and v dot is minus 3v minus 4x. We see that. So v dot is x double dot. So if we look at these two systems of equation, this is almost identical. This is identical to the original equation, which is the second order ODE. So from second order, by introducing a new variable v, we have reduced it into two first order ODEs, and that is something very similar we will do in the Hamilton's equation of motion from the Lagrange equation of motion. Okay, so this first example is more of a mathematical example rather than a physical example. So let us also look at an example arising out of pure physics, that is the case of gravitational attraction. So suppose we consider the orbit equations for a particle of mass m. Suppose we consider the orbit equation of mass m, and these are attracted by the gravitation. These are attracted by the gravitation of mass capital M, and they are fixed at origin. O. And let us say we write down the Lagrangian we'll write down the Lagrangian L of r comma theta, and we see that the Lagrangian in this case will be the kinetic energy, which is the following: r dot square plus r theta dot square. So this is the translational part and the rotational part, and then minus, so this is my kinetic energy, minus v, the potential energy will be minus of minus times m times capital M times g by r, right? And this is what we have, the Lagrangian. Okay, so in this case, the Lagrange equation of motion, this is a case of a conservative system, so we can directly use the conservative form of Lagrange equation of motion. This is an equation for two generalized coordinates r and theta. So we can write Vr to be, well, we can write the two Lagrange equation of motion. So Lagrange equation of motion. The two equations are, the first one is with respect to r, we get r dot minus r theta dot square. I'm just not showing you the calculation, that the final setup is shown here, minus mg by r square. And the second one is 2r dot theta dot is plus r square theta double dot, this is equal to 0, right? And we see that these are, so now both of these equations of motion are second order. First is second order in r, the second is second order in theta. So now the question is, can we reduce and write this equation of motion into first order equations? So then let me call this as 1. So let us now introduce new variables. Vr given by r dot and v theta given by theta dot, right? And we see that the second so what we find is the second order variables will reduce our equations of motion as follows. So we have r dot is equal to Vr and theta dot is v theta. From here we get Vr dot is rv theta square minus mg by r square, and v theta is minus 2Vr v theta by r. Okay, so this is directly from the Lagrange equation of motion, the last two. So now we have 4 equations of motion for variables r, theta, Vr and v theta. And that is how we reduce equations of motion from second order to first order. So then the next set of discussion is on the Hamilton's form of the Lagrange equation of motion. But I think at this point I am out of time. Well, we don't have much time to continue forward. So I will push it into our next module where we discuss the Hamilton's form of Lagrange equation of motion. So thank you so far for listening.